Okay, a lovely article again for those who don't like, non-technical experts to comment on these things. I'm not an expert on carbon capture and water harvesting from the air and so on, but this is a good topic, relates to climate solutions. I love climate solutions. I read it up, I learn enough to just give you a summary, very brief, leaving out all the technical details in fact, but you can always follow up if you are interested, right? So this is about distributed air capture of carbon dioxide, which we call, distributed direct air capture of carbon, what we call DAC, carbon dioxide by synergistic water harvesting. So you take out carbon dioxide typically through a flow-through system, but air also has water vapor. Can you also harvest water at the same time? And there are many companies selling these machines separately for harvesting water from the air. Many are installed in schools and so on. There are questions about how slowly they work, how expensive the water is, life cycle analysis, all those good things. Absorption-based direct air capture of carbon dioxide using chemosorbents like solid amines has been widely recognized as a sustainable measure to contain atmospheric CO2 concentrations. As you probably know, absorption versus adsorption. Adsorption is where a molecule adheres or sits on top of another material and forms kind of a membrane, and then you can move it or concentrate it and then do desorption to take it off, right? You probably know that already. However, the productivity and economic viability of DAC have been compromised by the high energy consumption for regenerating the adsorbents when you do it. There is the precipitation of CO2 from the air, where you take CO2 from the air and you convert it to calcium carbonate or something else, which is the precipitation of the CO2. Adsorption is when you just stick the CO2 molecule to something and then you desorb it, and then you want to be able to reuse the adsorbent. You can see I'm not a chemist, I'm struggling with this. Here we show that by synergistically harvesting water and carbon dioxide from the atmosphere, we can regenerate the unit using in situ vapor purge at low energy and capital cost. So the desorption of CO2 is substantially enhanced in the presence of concentrated water vapor at around 100 degrees C, concurrently producing 97.7% purity of CO2 and fresh water without the use of vacuum pumps and steam boilers. Moreover, we demonstrate that the DAC prototype can also be powered by sunlight, which recovers 98% of the absorbed CO2 with 20% less energy demand, enabling sustainable carbon capture from air in a real distributed manner. So let's get the basic gist of the idea. So read the introduction of why they are better than other methods and what the other methods are, and then we'll jump to discussion. There are very nice figures, very nice details of these reactions and so on, and the apparatus, and I'm skipping all that because if you want, you go learn it, and I'm not an expert on it either way. Among the various DAC technologies, the absorption-desorption process using solid adsorbents is particularly promising due to its relatively low generation temperature, which means you don't need energy to heat it up and so on. The selection of adsorbents and processes for DAC is constrained by the moisture and low concentration of CO2 in the air, which is around 400 ppm, 0.04%. So you'll have to move a lot of air to capture a bit of CO2. For physiosorbents like 13X zeolite, the air needs to be dried in advance to avoid the competitive adsorption of atmospheric water and CO2. The application of physiosorbents is constrained in cold conditions to reduce the energy consumption required for water removal. Therefore, chemisorbents, particularly solid amine sorbents, with large heat absorption 60 to 100 kilojoules per mole and high CO2 selectivity are commonly employed in DAC due to the promoted CO2 absorption under humid conditions. So if air is coming in with humidity and CO2 and you only want to select for CO2, this works better, the solid amine. However, regenerating chemisorbents is energy intensive due to the strong affinity of amine groups with CO2. Considering the required scale of DAC and deployment needed, the development of a regeneration technology with enhanced efficiency and reduced carbon footprint is essential for ensuring the sustainability of direct air capture. So selecting for CO2 preferentially is important, and then once it's absorbed, separating CO2 again from the adsorbent and reusing the adsorbent becomes an economic consideration as well. Typically, the generation of chemisorbents in DAC requires, the regeneration of chemisorbents in DAC requires elevating the temperature to above 100 degrees C using a heater and reducing the partial pressure of CO2 using a vacuum pump, both serving as the driving force for the adsorbent regeneration. So you want to remove CO2, then creating a partial pressure gradient can outgas it. To address this, temperature vacuum swing absorption TVSA processes are commonly used to achieve CO2 capture from the air. Nevertheless, the typical desorption pressure range of 5 to 30 kilopascals in the TVSA process can only release 30 to 50% of the absorbed CO2, resulting in low carbon dioxide productivity and hence a high capital cost. Okay, so temperature vacuum swing adsorption TVSA. To promote CO2 desorption and improve the working capacity, several strategies have been employed, including raising the desorption temperature, reducing the desorption pressure, and or implementing steam stripping instead of heating. However, these approaches result in elevated energy consumption as well as increased operating and capital costs, such as the expenses associated with the vacuum pumps. In particular, enhancing regeneration through high temperature steam stripping requires a designated steam boiler that not only increases the capital cost of DAC but also limits the potential deployment of DAC under various scenarios due to constraints of freshwater availability. Anything that demands more water is always going to be an issue unless you derive water during the CO2 adsorption process. So the objective of this study is to develop an alternative method to desorb CO2 in DAC, aiming to achieve a larger working capacity while minimizing energy consumption. In this work, we propose an in situ vapor promoted desorption VPD. This is vapor pressure deficit in ecology. So anyway, vapor promoted desorption VPD strategy to efficiently regenerate adsorbents and produce high purity CO2 and fresh water from the air without requiring vacuum pumps or steam boilers. There you go. This approach substantially reduces CO2 partial pressure during regeneration and recovers over 90% of the absorbed CO2 at 100 degrees C by in situ vapor purge using water harvested from the atmosphere. No new sources needed. We demonstrate this in situ VPD process by constructing a solar-powered DAC prototype that uses sunlight as the sole energy source for absorbent regeneration. This vapor-promoted DAC process achieves much higher CO2 working capacities in comparison with the prevalent TVSA techniques, reducing energy consumption and realizing a low total cost of $111 to $313 per ton of CO2. This is how everybody tracks it. How much is it going to cost per ton of CO2 to capture? In addition, the simultaneous production of water and carbon dioxide allows this DAC to be coupled with CO2 utilization process, further improving the economic feasibility of direct air capture. Okay. So let's just read their discussion. There are nice figures of solar energy and these tubes which are absorbing water and CO2 and then desorbing and so on and so forth. In this study, we developed a vapor-promoted DAC to achieve high CO2 working capacity with a low energy penalty through in situ purge of vapor synergistically harvested from the air. The process used double layered amine grafted resin and silica gel for absorbing atmospheric CO2 and water, respectively. During regeneration, water vapors dissolved from silica gel significantly reduced CO2 partial pressures, promoting the desorption of carbon dioxide. The stable CO2 working capacity maintained at approximately 1 millimole per gram after 9 cycles was achieved by in situ vapor purge at moderate regeneration temperatures of around 105 degrees C. In our VPD process, the temperature required to achieve a regeneration efficiency R was found to be determined by the molar ratio of equilibrium loading of adsorbed water to CO2, so N water over M CO2. This correlation was further used to predict the VPD performance under varying adsorbent volume fractions and feed air humidities. The vapor promoted DAC demonstrated operational flexibility across a broad range of atmospheric humidities in both arid and humid environments, effectively releasing over 90% of the adsorbed CO2 from the chemisorbent. Whenever we see CH, I always think chemisorbent at 103 to 120 degrees C. By applying a moderate vacuum of 50 kilopascals, the regeneration temperature was effectively reduced to about 85 degrees C. So you are taking energy on the pumping, but you are reducing energy needed for warming. To minimize the carbon footprint associated with raising the adsorbent temperature in regenerating vapors, solar energy was used to power VPD with a photothermal conversion efficiency of 63.1%. Even under low solar intensities of 600 watts per meter squared, around 98% of the adsorbed CO2 could be released within 50 minutes. So when you want to do this, solar energy will be the so-called concentrated power kind of system, not light harvesting solar PV panels. The energy consumption for VPD was calculated to be 10.3 megajoule per kilogram of CO2, significantly lower than reported TVSA and steam-assisted TVSA processes using the same CO2 adsorbent amines. More than half of the thermal energy was employed to increase the resin temperature and release the water adsorbed on silica gel. Compared with other electrically driven regeneration processes, the VPD provides a higher CO2 product purity and only requires low-grade heat to perform the desorption. The overall cost of the vapor promoted DAC ranges from $111 to $313 US per ton of CO2 and is sensitive to sorbent lifetime and heat costs. More research should be conducted to further reduce the temperature required to generate in situ vapors and to develop stable amine structures resistant to thermal degradation, so life cycle of the use of sorbent can be high. This work provides an alternative process for efficiently regenerating chemisorbents, concurrently achieving high CO2 working capacity and low energy consumption, demonstrating the potential to reduce both operating and capital costs of DAC. Okay, so it's a lab experiment with some scaled models in real world conditions of various levels of humidity in the air. What is the technology readiness level? How do you scale it up? How does it scale it up? And so on are yet to be figured out. Okay, so brief introduction to a very nice paper. Again, I hope you get enough information to learn something and follow up if you want. And remember, I'm not an expert in this, but I'm a climate scientist who is looking for climate solutions everywhere. And anything I find interesting, I'm going to tell you about it. Okay, see you in the next topic.